We all saw that. We all know what happened. But why did it fall? When I was in school, my physics teacher answered that question in 30 seconds. He wrote down Newton's law of gravitation on the board, asked me to memorize the formula, and moved on. And I did. I memorized the formula and I passed the exam, which was great. But what I didn't do was understand it. This is the video about what that lesson could have looked like instead. And at the end, I'll show you the tool I built so you can run this lesson in your classroom tomorrow. Let's start exactly the way you would start this lesson in your class. Just the experiment, no explanation. We all know where it went, but who can exactly tell why it even moved in the first place? Not what the law describes it, not what's in the formula, but how do you even think about a phenomenon, an observation? What's actually happening when you let the ball go? Before we test anything, we need to know exactly what we are even talking about here. To do this, first we collect all the variables that affect this system. Could be the air, which is around the ball, could be the mass of the ball, material of the ball, color of the ball, orientation, the floor on which it falls, the material of the floor on which it falls, maybe the dropper of the ball, maybe the planet we are in, the wind, the temperature around it. Everything is valid. Anything and everything that affects the system is a variable involved. Now, what affects and what we can control, what we cannot control is a different part. So the variables we can control become our investigation. If you're a teacher watching this is the moment most lessons skip. The variable step seems very slow. It feels like you're not teaching anything. But don't skip it, because this is where your students move from passive observers to active investigators. 5 minutes here saves 20 minutes of blank stares later on in your class. And from these variables, students generate questions, the real ones, which they can actually test and validate. Is Earth a giant magnet? Is there a huge column of air above the ball that's pushing it down? Is there an invisible force? Does the material of the ball matter? Does the shape of the ball matter? Does it have to be a ball? Can any object fall down or behave similarly? Every single one of them have been a serious hypothesis at some point in history. From everything that the students have come up, let's draw 4 hypotheses. Hypothesis 1. The Earth acts like a giant magnet, pulling down anything with a tiny magnetic charge or a metal content. Sounds plausible. Earth is huge and it can maybe pull things down if it's actually magnetic in nature. Hypothesis 2. The invisible weight of miles of air above us is constantly pressing down, pushing the ball toward the floor. Also reasonable. Air has weight. We live under a column of atmosphere above us. So maybe it's just pressure? Hypothesis 3. Objects fall back to the same height they were picked up from in order to conserve energy. This one sounds almost logical. Energy is conserved, we know that. Maybe it's the universe correcting the imbalance. Hypothesis 4. There's an invisible tether, a force of attraction between the mass of the Earth and the mass of the ball, pulling them together. This fourth hypothesis encompasses all the other hypotheses in the sense that there is no variable involved that is affecting why things fall down. We're just saying everything that has mass falls down. 4 explanations, all of them internally consistent. The question is which one survives the test. 1 experiment per hypothesis. Let's go. Investigation 1. The magnetic Earth. You can drop a plastic ball and a metal ball and see if either of them fall down. We see that both of them fall down at the same time. If Earth were a giant magnet, it should not have affected the plastic ball and it should have stayed in the air. This says that our assumption that Earth as a giant magnet is pulling everything metal towards it is wrong. Let's move on to investigation 2. The atmospheric push. Hold the ball in contact with some sort of a ceiling. Here, I've taken a book. Because the book is held tight, there is nothing above the book that can push the ball below it. And now we try and drop the ball. We see that the ball falls even if there is nothing above it to push. Let's move on to investigation 3. The energy return. Place a ball on the table. pick it up and drop it. Now take the same initial condition, place the ball on the table, pick it up, remove the table, and now drop it. So if energy were to be conserved according to the hypothesis, the ball should have fallen up to the height of the table and stayed there because energy is conserved. But what happens is the ball falls through and hits the floor, which is an even lower energy. This shows that things need not come back to the same height that they were at. There's something more to energy conservation than just returning to the same height. This shows that the hypothesis 3 of energy return is not correct. To test the last hypothesis, let's compare as many variables as we can control. Let's see if the texture of the ball matters. Both balls are yellow and the texture is different, and we let them fall. Both of them fall down, showing that the texture does not matter. Maybe the color matters. So these are two balls of different colors, and when we let go, both of them fall down again. Here we have tested also the size difference, the material difference, the color difference, the texture difference, and so on. And none of them really affect whether the ball falls down. There's always the same result. It falls down in a straight line. As a teacher, you might be thinking, aren't there more hypotheses that we can build out of it? And I'd say yes, you can build hundreds of hypotheses from the variables given, but this is a classroom, and you know better than me that the time is limited, and it's up to the teacher to determine which hypothesis to test in class, which is testable in class even. The idea is not to elaborate on the exhaustivity of this list of hypotheses. The idea is to instill in the student's mind that there is no one simple correct explanation straight away. There is an observation, there is a scientific methodology that people have followed throughout the history to arrive at conclusions, to draw theories and laws and write equations. So once they do this, they get a sense of scientific temperament, which they will use hopefully when they look at other phenomena in their lives. So coming back to our experiment, there were 3 wrong options, one partially right option, partially because this invisible tether idea is giving us the right direction of where the object is moving, but doesn't exactly explain how or what is it even dependent on. Is it completely independent of everything? That's where the details comes in. So what is this invisible tether exactly? Newton gave us the answer, and it is more interesting than it sounds. First, the equal tug. When the ball falls towards Earth, the Earth is pulling the ball towards its center. That's intuitive. But what's counterintuitive is that even the ball is pulling Earth towards its center with exactly the same force. Newton's third law applies to gravity as well. The ball and the Earth are tugging each other equally. So why does the ball move and not the Earth? It's because of Earth's mass. It's 6 times 10 to the 24 kilograms. Same force applied to that massive object results in an acceleration that's negligible. The ball with almost zero mass compared to the mass of Earth gets launched towards it at the rate 9.8 meter per second squared acceleration. Same force, completely different outcome. This is the mass inertia paradox. It's one of the most underrated ideas in school physics. Now the formula. And I want to talk about what each variable or constant mean here, and not just term it as some letters, a combination of letters and mathematical expressions. G is the gravitational constant. It's a constant of proportionality, and it's minute. Its magnitude is of the order of 10 to the minus 11. That's how small it is. And no wonder gravitational force is the weakest of them all. Just a small fridge magnet pulling a paper clip is overcoming the entire gravitational force of Earth on this paper clip. So G tells you how weak or strong the gravitational force actually is. Next, coming to the masses. So the 2 m's that you see in the formula are the masses of 2 objects. I say 2 because that's how many objects that you need for gravitational force to act. So force acts between 2 objects. In our case, it was the Earth as one mass and the ball as the other. So these are the two masses. And there's another variable that's involved, which you can see in the denominator, which is r. R is just the distance between these two objects. So yeah, it's just two things that the gravitational force depends on: the mass and the distance. Masses of two objects between which the gravitational force is acting, and the distance between their centers. What's important here is that the gravitational force is dependent as a square of the distance, or quadratically. This is crucial because now if the distance between the two objects is halved, then the force doesn't just become double, it becomes 4 times. This is called an inverse square law, and it shows up everywhere in physics. But here's the teacher's secret. Again, this formula from Newton's law of gravitation tells you the magnitude of the force acting between the two objects. But it doesn't really tell exactly what gravity is. In 1915, Einstein showed that gravity is not a pulling force at all. Mass curves the fabric of space itself. And the ball doesn't fall because something is tugging it. It's just moving in the straightest path possible in a curved space. That's the whole saga. It's worth noting that it exists because when a student asks you why mass attracts mass, Newton doesn't have an answer, but Einstein does. When I was a student, nobody showed me any of this. I just got the equation, I memorized it, and then I passed the exam. And something magical happened. Well, I forgot everything right after the exam. What I remember from school is not these equations. It's 1 or 2 moments when the teacher really surprised me, maybe brought an experiment to class, maybe the time when we played with the liquid nitrogen experiment, the one experiment which teachers did in class, so we were hooked, right? So these are the things we remember. That's what this structure is designed to create. Not more memorization, but genuine spark and curiosity. These are the Inquiry Saga cards. The gravity lesson you just watched is pre-filled and ready to print. You don't need to design anything, just download, cut, and run it in your next class. The link is in the description, along with an empty template so you can build your own saga for any topic. Try it, and if a student asks a question that you were not expecting, that's the whole point. Subscribe if you want more of these, and see you in the next video. Hey guys, if you're still watching, thank you for sticking around. The Inquiry Saga cards that I have built is for teachers like you to facilitate scientific inquiry in your classroom. This is only the beginning. There are many more to come. So the first edition with the empty template and the pre-filled Gravity Saga that you just watched is available completely for free, and you can download it in the description. I hope you can use it in your classroom and also maybe share it with your fellow teachers and let me know what they think about this. So if you have any questions on how to use it and what this is, please drop a comment or maybe even send me an email.